Okay, this is Physics 2211, Lab 1, Constant Velocity. So the purpose of this lab was to model constant velocity motion using a real-world model as well as a computer-generated model of position over time. The fundamental physics principles were constant velocity motion and Newton's first law, since we're dealing with constant forces. A brief preview of the results. The actual results of position over time will differ slightly from the results from the computational model due to unavoidable interactions with real-world forces such as friction and air resistance. So our model describes a perfect world where all the forces cancel out, but in our real-world situation, all the forces probably will not cancel out. The main physics ideas we were looking at were the position update formula, which is stated on the left, the velocity update formula right underneath it, and since we're using constant velocity, the net force will cancel out to 0, and the average velocity will equal the initial velocity, since in the velocity update formula, that whole component with F net over m will cancel out to 0, since the net force is 0. And our system we're looking at is the expo marker. Our surroundings are the hand that applies the force to the marker, as well as the surface that it is rolling on, gravity, and anything surrounding the system. So I drew a couple free body diagrams to demonstrate the forces. During the push, we have 3 forces: the gravitational force, the pushing force, and the normal force, which makes it move in a direction. And while rolling, the forces cancel out since it's constant velocity, so we only have the gravitational force and the pushing force. Okay, and here is the video of my tracker simulation. Our key assumptions made: we ignored the air resistance on the object and any force of friction. We also ignored the movement in any direction other than the x direction. Okay, from our tracker simulation, we can get that our initial position was the vector 0.0140600 meters, and we can calculate our velocity because we know that the initial velocity is equal to the average velocity, and that the average velocity is the change in r over the change in time. So we can take our initial position, which is listed there, and subtract that from our final position, also listed, giving us our displacement, and then we can divide our displacement by our change in time to find our velocity, and our velocity ended up being the vector 0.03200 meters per second. For our purposes, the mass of the marker doesn't matter, since the only time that the mass appears is in the velocity update formula, and since the net force is 0, the entire factor that includes the mass will equal 0. Our initial time from the tracker was 1.3 seconds, and our time step was 0.033 seconds. This is the code that I used to model the motion of the expo marker. The code that I edited is highlighted in yellow. Lines 35 and 36, I added the initial position and velocity values that were calculated on the previous slide. Lines 39 and 40, I added the initial time step and the time step values. Line 51, I added the final time stamp. Line 54, I moved the print statement to include my initial conditions because before it would change my values without graphing the initial conditions. Line 56, I kept the net force equal to 0 since it's constant velocity motion. Line 60, I used the velocity update formula, but I kept the velocity the same since there's 0 net force. I used, on line 61, the position update formula with average velocity and the time step. Is the output of my code. As we can see, the position over time graph is very linear because it's constant velocity, and the velocity versus time graph is constant because constant velocity, which means there was no acceleration during this simulation. The data from my computational model, I made a graph of my observed and predicted results. So the observed results are in blue and the predicted are in red. So they have the same general trend and the same y-intercept, but the predicted graph is more linear since it was generated by a linear equation, the position update, rather than observations in the real world. The initial velocities of the observed and predicted models are very similar. The speeds diverge slightly during the simulation, but not by a great margin. The speed of the experimental object becomes slightly greater than that of the predicted object, which suggests a net force acting on the object in the direction of its motion. Possible sources of error include slight differences in the placing of the center of mass within the tracker simulation. This would affect the position. The surface we conducted the experiment on might have not been entirely level. This would also affect the position and might give it a little bit of an acceleration due to gravity. And there also might be rounding errors during calculation that might be a possible source of error. And now the what if question. What if we flip the axes? The direction of velocity and the position would become negative, and the graph would have a negative slope. Since only the value matters in the magnitude, not the sign, the magnitude would remain the same. What does it mean? Is it possible to say how many forces were being added together to give a zero net force? No, the only forces we know for sure are gravity and normal force. We cannot say for sure whether or not there are other forces acting on the ball. We can only determine there was a constant force acting on the ball because we observed a constant velocity. Okay, thank you for listening. Bye.